Alright, hell yeah. So we have JEE main. This is 2018. Now I just Googled, you know what I mean, PFD questions or PDF, and this came up. And this one had solutions, but man, you know what I mean, I get it. Everyone's just got technical solutions for these problems. And this one involves collisions. So I'm gonna go over, and I'm gonna try to do this as fast as possible. You know, we're not gonna try to make a 3-hour video. Hopefully just 30 minutes. But I spent about an hour going over this, and I was just like, all the equations, because you have to know like coefficient of restitution, and for elastic collisions it's 1, and you're like, what is this number? Well, it can be a number between 0 and 1. It can't be more than 1. And so, and the definition like spells it out. It's almost better just to use the definition and go from there. The definition says, well, let's set up the problem too. You know, this problem's awful because we're talking about a neutron. You know what I mean? But you know, a neutron has an atomic mass of 1, and then you're going to hit a deuter, you know, whatever that says. But it's a duo, and so that has 2. So it's going to be like a hydrogen atom, maybe with 2. Maybe it's got 1 proton, 1 neutron. I have no idea. But anyway, you're coming in with a mass of 1, and you're hitting something with a mass of 2. That's it, you know what I mean? And then this thing is going to be at rest, so we have 0 velocity here, and then we're coming in with a v naught, you know what I mean? So that's it. And what we want to know for this coefficient of restitution, and where you would find this in the problem, is just from this word elastic. If something is elastic, the coefficient of restitution is 1. Nothing can be partially elastic, so I had to look that one up, because if something's 0.5, let's say E is 0.5, well, that's going to be partially inelastic, and if this is 0, that's totally inelastic. And I'm going to go over that, because there's a lot of confusion, I think, because they say if something's inelastic, you lose all kinetic energy. And it's just like, well, you technically don't lose energy in the sense that, you know, you can only transfer energy. You know what I mean? From one thing to another, you can't create nor destroy energy. So we're going to talk about that as well. But basically, the definition of this term, coefficient of restitution, and hopefully I said that right, coefficient of restitution, that's going to be E. And maybe I just called it the coefficient of elasticity, but it's coefficient of restitution. Hopefully I'm saying that right. But what if it's 1, that means that the relative velocities between the incoming things that are going to collide are going to be the same after it. That's all, you know what I mean? And so if we have a relative velocity, if this one's stationary, this one's coming in hot, v naught, then when they collide afterwards, let's say this one just stays put, you know what I mean? So we have this this mass just has a 0 velocity, and then this one, like with a coefficient of restitution of 1, then this 2m would have a velocity of v naught. You know what I mean? Now their relative velocities are the same. So that satisfies this, but now here's what I would do. Like anytime I get a collision problem, you might as well run through 3 scenarios. And run through a scenario where the coefficient of restitution is 1, then do 0 and 0.5. And I'm not going to say coefficient of restitution. I'm just going to say coefficient of elasticity. But anyway, and because this should strike you, this scenario right here cannot happen. You can't come in because you're satisfying 2 different things. Sure, in a collision you can have, you know, 0, 0.5, 1, and anything in between happen between the 2 colliding particles. All right, but what you can't have is you can't have your momentum initial, you know what I mean, has to equal your momentum final. Unless you're losing momentum to heat or, you know, vibration, because basically it's for all these problems, this is kind of a cool law, like a Newtonian law. If I have a mass and it does have some sort of velocity, the only way I can change this velocity is, applying a force. Force equals mass times acceleration. If I apply a force, hell yeah, I can change that velocity. That's the only way. And with that said, all right, and let's take a look at this, because this is kind of fascinating. Let's say you're on the Earth, most of us are, and then you jump. So you're like this, but then you kind of jump up into the air. If you, so what we have going on here is that you do have a mass. You apply a force downward against the Earth that basically pushes your body upward. You know what I mean? So you're kind of putting an equal and opposite force. You're pushing down into the Earth. The Earth pushes against you and sends you skyward, however that works out. I guess what I'm getting at, though, is that as you move up, let's say you apply a force of, I have no idea, because, all right, no, we got this. All right, so F equals ma. This is kind of a side thing, but you have to apply a force that's so if you weigh 70 kilograms and gravity is 10, you know what I mean? The force, like your weight, is going to be 700 newtons. So you have to apply a force that's more than 700 newtons. To get a change in velocity. But if you apply a force that's 1,000 newtons, hey, maybe you'll pop off the ground. But when you do that, all right, hell yeah. So when you do this, the Earth moves that way. Like, you're going to move upward, but the Earth moves this way. But it's proportional. The Earth is huge chunk of mass, and you're just a little chunk of mass. And so what happens is that somewhere there's a center of mass of the system before you jump, and then after you jump, the center of mass of that system doesn't change. And so what happens is the Earth has to move down this way. You know what I mean? So the center of the Earth is here because now you're skyward just a little bit. You know what I mean? And it's obviously not going to be much at all, but this principle works for in any sort of mass. I mean, you could just have one atom, you know what I mean, being forced away from the Earth. The Earth is going to adjust its location. But so minutely, you're not going to be able to tell. All right, so that was a horrible demonstration of just like, hey, conservation of momentum. And I guess F equals ma, but what happens is when you do collide two particles, you generate a force, but it's going to be an equal and opposite. All right, I don't want to say anything I would regret, with equal and opposite force, but your momentum before has to equal your momentum after. So we're going to come in with a v naught on this mass m. We have this 2m right here. We're going to collide into it, and this has a velocity of 0. And so the initial momentum is like mass times that v naught. Cool. And this has to equal the final momentum. So now just like pick some scenarios. Let's pick the scenario where this mass, so we're going to say, hey, this mass is 0 velocity, and then this 2m, we're going to do that scenario where, hell yeah, now it has an initial velocity of v naught. And that satisfies this coefficient of elasticity being 1. Because the relative velocities between these two were v. Now we're going to get the total wrong answer, but this is kind of a cool way to tackle this problem, to kind of learn how these things work and be like, oh yeah, now I get why this scenario can't happen. Because you can just see linear momentum. How did we come in with one mass with a velocity and then have this mass go stationary and then leave with twice as much linear momentum? Because the linear momentum here is a quantity of 2m times v naught. And momentum, just as a number, just as a quantity, an amount, this is a mass, 1m times v naught. And this linear momentum as a quantity is twice. So we can't have that. So now we did satisfy the fact that the coefficient of elasticity was 1. So now let's dial it back. So we're gonna have this mass come in with V naught. We have the 2m right here. It's stationary. And then we're going to collide the two particles. We're going to choose a coefficient of restitution of 0.5. So, and you don't have to get too creative with this. We're just going to say, hey, this mass of 1 stops again. But then this mass has a velocity of just 1/2 v naught. So we have 2m with a mass of 1/2 v naught. And hell yeah, it seems like we're doing pretty good here. So so now this would be a coefficient of elasticity of 0.5, meaning that the relative velocity afterwards is going to be half the relative velocity between these two incoming. And it's pretty cool because now our momentum is the same. We have an incoming momentum of v naught m. And then leaving, this doesn't have any momentum, but we're going to leave with a momentum of 1/2 v naught times 2m. So that's going to be m v naught. You know what I mean? That's going to be 2m times 1/2 v naught. You know what I mean? So that's going to be, so the momentum coming in is going to equal the momentum going out. So we do have a check on reality there, but it just doesn't satisfy the elasticity of our problem. We have an elasticity where the coefficient of elasticity is 1, and this represents the most, they say most bouncy. It means that the relative, and again, it's just back to the relative velocity. The relative velocity coming in is a difference between these. It's a v naught. This is 0, this is v naught. And so the relative velocities going out have to be 0 and v naught. Alright, hell yeah. And so this totally fits my style because I would just rather play around. Like, I would just rather know like 1 or 2 simple definitions. One is that linear momentum has to be conserved. And then 2, you have this idea of elasticity. So let's go back to kind of the Earth. If we have a bouncy ball, we can basically say the Earth has a velocity of 0. And then we're going to drop this bouncy ball, and it's going to have a max velocity when it hits. And if we have a coefficient of elasticity of 1, then the relative velocity after the impact is going to, send it up the same distance, and it must have the same velocity. So the velocity upon impact right here is v naught, and then we're going to say after impact, the velocity right here is going to equal, the velocity final is going to equal v naught. So, and that says the relative velocity between the Earth and this thing coming in, like right before it hit. I mean, obviously gravity. You could drop it with 0 velocity here, but you really have to look at this scenario right before impact. So here's the Earth again. Right before impact, this thing's coming in with a v naught. And then, so that's the relative velocity. Earth has a 0 velocity. Velocity is 0. So the relative velocity between these is v naught. And then so after the impact, the relative velocity between these two things, well, is v naught again. And so this thing's now going up at v naught. And so that satisfies this idea that the coefficient of elasticity is 1. So we could do this scenario where E is 0. You know what I mean? We're going to drop this ball, and then right before it hits, it's going to have a v naught. And then once it does hit, it's just going to, let's draw one more. It's just going to embed itself into the Earth and stop. It's not going to have any velocity. It's not going to have any final velocity up. So this is a scenario where the relative velocity between the Earth and this little object is 0. There is no velocity between them. They're totally stuck together. So that's the scenario where the relative velocity is 0. And I mean, if your bouncy ball only bounces half as high, well, the Earth ain't going nowhere, even though we just said that if you jumped up off the Earth, it is moving that way, but it's moving in such a tiny amount. Because linear momentum says, like, it would be like this. If you have the Earth and then, a chunk of mass comes in and hits it, You know, just like, let's say, I don't know, just like a baseball-sized chunk of mass, which is 0.1 kilograms, comes in at 50 meters per second. So now you have a momentum of 0.1 kilograms times 50 meters per second. You have a mass and a velocity. And so you have a quantity here of 5. So that number 5 is going up a... so we have a mass and a velocity. This number is 5. That has to equal the linear momentum. And so let's say it actually just sticks to the Earth. You know, it kind of sticks into a pile of sand. Coefficient of elasticity is 0. Coefficient of restitution is 0. The Earth now gains 0.1 kilograms. That's negligible. But we have the mass of the Earth, which is so massive that to get... So we had like 0.1 kilograms. I mean, the mass of the Earth is 10 to the 24. You know, 6 times 10 to the 24 kilograms. And so this number is so monstrous that how are we going to turn this number into 5? Well, you would have to multiply it by a number equally... I mean, you would basically have to multiply it by 10 to the negative 24 meters per second. And so, hey, check that out. 10 to the 24 divided by 10 to the 24, that's going to be 1, and then we got that 6. So, hell yeah, this is a scenario just real fast that you could just find the velocity of the Earth. You throw, you know what I mean, you throw... yeah, you throw a fastball downward at the Earth. I don't even know if that makes sense, because I think the second you actually throw it off a platform, you're actually, I think it cancels itself out anyway. But yeah, if you have an asteroid that's the size of a baseball, weighs the same as a baseball, and hits the Earth at 100 miles an hour, the Earth is going to move that way with a velocity because linear momentum has to be conserved. You know what I mean? So if we get pelted with something and it hits the Earth, yeah, linear momentum is conserved. And we can talk about the scenario where, I don't know, let's say it's possible for a baseball chunk of thing to come in and impact the Earth and for whatever reason bounce the other direction. And bounce off the Earth, but only with half the velocity. So E is 5. E is 0.5. And, well, you're still going to... so the momentum of this went from 0.1 kilograms times 50 meters per second on the way in. On the way out, it turns to 0.1 kilograms times 25 meters per second. And now you have a momentum of 2.5. So you had a momentum of 5 going in, so keep track of that number, and then 2.5 exiting. So that means that the Earth has to have a momentum this way of 2.5. That number's got to be 2.5, so we need to divide by 10 to the negative 24, and, I don't know, divide by, like, 3. So we would have to divide by 3 times 10 to the 20. That is the velocity of that baseball. Would be 1/3, or it would be 0.3, or it would be 3 times 10 to the negative 25 meters per second. So it's kind of cool, even with scientific numbers. I don't even know what you call these numbers, but anyway, that you can estimate, you know, how much velocity the Earth's going to move, just because, yeah. So I think we're doing a pretty good job so far. Alright, hell yeah. And I know we're doing a good job because not once have I ever had to bring up the equation of coefficient of restitution being like, oh yeah, so coefficient of restitution says we have the velocity of the thing leaving, you know, the velocity of this mass, we're going to call that V2 final, minus the velocity of this mass final, so V1 final, divided by... Now we have to switch it. We have to say the velocity, the incoming velocity, V0, 1 initial, minus the initial velocity here, and that's V2. You know, look how many little characters. And you want to do your initial velocity with U. That's going to be kind of what they do. This is object 1. This is object 2. And you're not finding the difference. You're taking the first minus the second. And then this is the second minus the first. And this is going to be the coefficient of restitution. And so But you're typically used to writing things like the second, like the difference between them. So the difference between them is the second minus the first. And so how you write this equation would be, if you do bring this upstairs, so you would have V2 final minus V1 final is equal to E, and then just bring it upstairs. That's all I'm doing. E1 initial minus E2 initial. And like even right now, you don't even know what these things are anymore. I think capital V, these are your final velocities. Object 2 final velocity, object 1 final velocity. But I would throw an F on these just so you don't lose your mind. And then the U's, these are your initial velocity of object 1, initial velocity of object 2. But might as well throw an I on there just to know they're the initial velocities. Now, because this is 1 minus the second, you might as well flip it around and find the difference between them. So this is kind of what we do, and you say the second minus the first. And if you do that, well, then you have to make this E negative E. So this is how they do this equation. But how awful. What an awful equation. Even right here, you're never going to remember that either. So like, I don't think you really need to. Alright, hell yeah. So now we're going to do kind of the guess and check method. It's kind of the best way to learn, because then you get to do like the problem like 4 or 5 times. So we're going to have this mass coming in with a velocity initial. It's going to hit a mass that's twice as massive. And then we're going to, after the collision, we need that coefficient of restitution. The difference between these velocities has to be 1. Well, no, we're just going to do it with equations. But now, the second part of this problem is to set up the linear momentum. So incoming, we have a linear momentum of 1 mass times this velocity initial. Cool. That's the only momentum in the system. This thing's not moving. If they were both moving, we would say that we would want to know the momentum of both objects. And then after they collide, we want to know the momentum of both objects. Cool. All right, so we're going to say the initial momentum of this object after the collision has to equal whatever the velocity is afterwards. So afterwards, we're going to have, and in the problem, I don't know. They don't do a very good job of I'm not using U's. I'm just going to do it. I'll show you their solution at the end maybe. But yeah, so what they say is, they do this. They say you have this mass and this mass. This is the initial setup, and then afterwards you have this mass and this mass. So this is 2m, this is m. You have an initial velocity of initial. This is 0, and then for their notation, they're going to call this v1, and then they're going to call the velocity on this one v2. Sweet. And they're just going to choose this as the positive direction. And I think that's smart, because we're gonna run across some negative numbers, and I think you already saw that. Because if this mass hits this and stops and transfers its linear momentum, this mass will have a 1/2 v naught. You know what I mean? So because we'll have this twice as mass, but we'll half the velocity. But this would be a coefficient of restitution of 0.5, because the relative velocities are 0.5, and so we can't have that. This is a check on linear momentum, but we need this to be we need the difference between these after the collision, the difference between these velocities, to be v naught. And we just did the scenario where if this one hits and stops, and this one has v naught, it'll have twice as much momentum. So that can't happen. So that should set you up for like, hey, when this collides, this one bounces off. And I was thinking that was the case. Just like if you have the Earth and you have a bouncy ball with the elastic of 1. You know what I mean? This is also a ball, and then you have a bouncy ball that hits the Earth. Now it just instantly bounces back. But But in this case, we don't have a mass the size of the Earth. It's just twice this mass. So sure, this mass is going, this will bounce back, but then this will actually drive forward as well. All right, hell yeah. So now let's just use the equation. So we have this, so now that we just labeled that this final velocity of mass 1 is going to be v0, and then we have v2. That was just kind of the labeling. So the initial momentum has to equal the final momentum. So the final momentum is going to be mass times v1 plus 2 mass times v2, because this is twice as massive, so that's that mass, and that's its velocity. Okay, so we have to satisfy this equation, but then we also have to satisfy the equation that the difference between these two velocities have to equal this initial velocity. And so because we spelled out we spelled out the definition of coefficient of restitution or coefficient of elasticity, or where E is 1, now we kind of know that from the definitional standpoint that, hey, what's the difference between the velocities coming in? That has to equal the velocities going out. And then you can just get to your easy equation where you can say, okay, the difference here is v0, and that has to equal the difference between these two, which is just v2 minus v1. And now we're on a roll, you know what I mean? And we can even take this linear momentum equation and drop out all the masses. So now we have this equation. So this equation turns into v0, v1 plus 2 v2. Now, and this is where these problems suck, because we have kind of two equations that are really similar, and you're just like, what are we even doing? You know what I mean? So now we kind of have to go back to look at kind of what the problem. But I think this was the hardest thing for me to be like, oh, I haven't done this stuff in years. And actually, no one actually taught me this. So it's just kind of cool, like going back and studying and be like, well, what is this? And you might as well pick 3. You know what I mean? Pick a scenario where, and yeah, let's do one more. Let's do a scenario where, like this, it perfectly connects with this and is perfectly inelastic. So when this mass hits this 2 mass, like all 3 go. So you're going to have so the momentum you're going to have v0 m coming in, and then leaving you're going to have m plus 2m. So those masses are going to combine, and then you're just going to have a v0 leaving. Or you would say this, you would have mv1 plus 2mv2. That's kind of how we have it written, but we're going to say that v1 is equal to v2. That is the scenario where these two things mesh and their velocities have to be the same. So if you do that, you can just choose either one you want, and you could say that's like 3, we'll just do v2, so we have 3m v2. So v0 m is equal to 3m v2. Now you can see that v0 is 3 v2, but we want to solve for v2, so you would say v2 is 1/3 v0. So that's the scenario where if they are perfectly sticky, linear momentum has to be, conserved. The linear momentum initial. So the momentum initial has to equal momentum final. Momentum is just mass times velocity. Additive. This thing's at rest. So, you would add it if it was moving too to this one. That would be your total. If they're both moving, they both have linear momentum. If they collide, then you have to make sure the final linear momentum matches the initial linear momentum. Okay, hell yeah. And this was good because just doing that, then you get like, oh, okay, so if they do collide, this final velocity is going to be 1/3 v0. Okay, sweet. So now when we go back to our scenario where we have an elastic collision, we know that this mass is going to bounce back that way. We're still making its velocity in the positive direction, but we're expecting this to be a negative number. So and we understand what this term is because it's just the difference between those two masses. So v2 minus v1 has to equal this v0. And now you can see that, I don't know, could we spell it out? Because if, well, Well, when one, we know that when this mass hits this mass, this thing ain't going with V naught. It's going to go with something less. You know what I mean? So if this V2 is something less, if this is like 1/2 V naught, well, what would this have to be? You know what I mean? 1/2 V naught minus something is equal to V naught? No, so V1, like this has to be traveling in that direction. So we would have to have minus a minus. And this would be minus a minus a 1/2 V naught. So that would be a scenario where that would be a check where, you know what I mean? If this hits this, and let's say this goes 1/2 V naught that way, and this one rebounds at 1/2 V naught that way, but we'll do a check on momentum, and you'll see the check on momentum won't happen. So that's still not the answer, but it's good to just do 1,000 different problems. If we did have both these after the collision going at half the initial velocity, the momentum on this one would be m. It would be 1/2 mv v naught, and the momentum on this one would be 2, well, it would be 1/2 times 2 mv naught. So we would have the initial would be 1/2, and then the final would be 1. So that is not, momentum would not be conserved. So all right, let's just crank out these. We got 2 equations, 2 unknowns, so we can solve for both V1 and V2. So what do you want to solve for first? We could say that. We could do this. We could solve for V2 right here. We could say V2 is equal to V naught plus V1. And then we're going to shove this into this equation. And sometimes it is useful to just be, well, we're going to multiply by 2. Let's just do that right now. So we're going to do 2 times this equation. That's going to be 2V naught plus 2V1. And now we can shove this right into there. And then we'll solve. So we've got V naught is equal to V1 plus... and then we got 2V naught plus 2V1. So sweet. So it looks like, and we need to take this V naught to this side, because then we'll take 2 minus 1, and then we'll just have 1 over here. So let's do that. And then we got to take all these. We got 3 V naught over here, but we got to take them to the other side. So we got negative 3 V1. I'm sorry, I needed to say V1 on that. So we got 3 V1, take it to the other side. We're going to subtract V naught here. So we got V naught is equal to negative 3 V1, and we want to solve for V1. So we got V1 is equal to negative 1/3 V naught. And hell yeah. So now we know that this one is traveling in that direction. We know it's traveling by 1/3, and we can solve for the other one. We know that using the same equation, V naught is equal to V2 minus 1/3 V naught, and let's solve for so that's going to be basically plus 1/3 V naught. So we got V2 plus 1/3 V naught is equal to V naught. So we're going to take this 1/3, subtract it over here, and we're basically solve for V2. So V2 is equal to this 1 V naught minus this 1/3. That's going to be 2/3 V naught. Hell yeah. So now after this elastic collision with the elasticity of 1, this thing's going to be going 2/3 V naught that way, and this thing's going to be going negative, or just this way, by 1/3 V naught. And now we can do the momentum. The momentum of this one is going to be 1m 1/3 V naught. Now it's going in the opposite direction, but it doesn't matter. We're just trying to find the absolute value for the momentum, and so and then that has to equal the momentum of this one. And this one, did I even do this right? Oh, yeah. No, I did. My bad. I'm just getting a little bit, need more space. So the conservation of momentum says the initial setup, we have this mass, we have mv naught. That is the number on momentum coming in. This 2 mass doesn't have any velocity, it's just 0. So this is the number coming in. The number leaving is 1/3 mv naught from this one going that way. And then this one is am I doing this? Oh, yeah, no, this is interesting. No, so wow, see, I'm bad at this. No, the direction is important. So if you have, oh, that's fascinating. So if I have this initial mass coming in with a velocity this way, and then it hits a stationary object, but bounces back this way, you know what I mean? So the momentum does have a direction. It has a magnitude and a direction. So we have, the total momentum of this system is going in this direction at mv naught. And so after the collision, when this is going, 1/3 mv naught in the negative direction, and then this 2 mass is going at 2/3 mv naught in the positive direction. Wow, yeah, I've not done a whole lot of these problems, but the total momentum is going to be, this one's going to be negative. We have negative 1/3 mv naught. And then we're going to add it to, the velocity on this is 2/3 v naught, but the mass is 2m. So we're going to multiply these together, and we're going to get 4/3 mv naught. So we have negative 1/3 mv naught plus 4/3 mv naught, and that gives us 3/3 mv naught, or just mv naught. So there you go. We have a check that the final momentum is equal to the initial momentum. Brutal. And holy hell, that was just to, that was all that was to get the velocity. And now kind of the crazy part. So let's do this problem a little bit faster. But might as well kind of just do it the same. And let's set it up just like they do. So we have m, 2m, v naught. And then leaving, we're going to have v1 and then v2. Coefficient of restitution is, hopefully I'm saying that right, but is 1. So that means that the difference between these two, so we have v2 minus v1 has to be this v naught. Hell yeah. And then we have momentum. The momentum coming in is mv naught, has to be equal to momentum leaving, which is mv1 plus 2m v2. And so here's our equations. We changed this equation. We dropped out the masses, so we just had v naught plus 2 v2. And hell yeah, I guess, yeah, might as well solve it again. If you can solve it once, you're just like, it's such a head scratcher even to solve it again. But what do we want to solve for over here? We wanted to solve for v1. So v1 is equal to v2 plus v naught. But anyway, it doesn't matter how you want to solve it. And so let's just throw that into this equation. We got v2 plus v naught plus 2v2. I feel like I'm making a mistake here. Because v1, never mind. Yeah, if we solve for v1, that's going to be v2 minus v naught. Sorry about that. I hate negatives. Yep, because if I'm solving for v1, got to go to this side. This has to subtract that side, v2 minus v naught. Okay, and then we throw this one into this equation, and we get v2 minus v naught plus 2v2. So we get 3v2, and then we're going to take this v naught to the other side. So 2v naught is equal to 3v2, and we can say that v2 is equal to 2/3 v naught. And then we'll throw it into whatever we want to solve for v1. So v1 is 2/3 v naught minus v naught. And so that's going to be 3/3 minus 3/3 v naught. That's 1 v naught. So we're going to have negative 1/3 v naught. So hell yeah. So there's v1, and then there's v2. Okay, so now this problem is 2 parts too. It's just like holy hell. And these come up a lot. So we found the velocity going in for like the first particle, and that's what we're trying to find. So the neutron comes in, the mass 1 comes in with the v naught and leaves with a negative 1/3 v naught. So it definitely changes velocity. It changes direction, and that's not the big deal. Even if it came in and hit a wall perfectly elastically and came in with v naught and then left with v naught, its kinetic energy would be the same. It would still be a molecule going across, or an atom, or a neutron going across the universe with a mass and a velocity, and that didn't change. Even though it changed direction, it still has the same quantity of momentum. It has a mass, and it has still that same number for its velocity. And that's what we attribute. We attribute that to momentum. We also attribute this to kinetic energy. So kinetic energy is the equation 1/2 mv squared. So coming in, initially we have a kinetic energy of 1/2 mv naught squared, but leaving we have a kinetic energy final of 1/2 mv so for this one it's mv1 squared, and we just said that mv1 is negative 1/3 v naught. Now we're going to square that, so we could say v1 squared right here is 1 divided by 9 v naught. And sometimes squaring fractions, you're like, how did you do that so fast? So if we have 1/3 and we're going to square it, it's really good just to like hey, I can square each thing in here. You know, it would be the same as saying 2 times 3 squared. That's going to be 6 squared is 36. But how could you do that? That's going to be 2 squared times 3 squared. And this is going to be 4 times 9. Hey, that's 36. So just, you can always, you can take whatever number is in here and get it into a more basic form. I mean, you could do whatever you want to this. You could say this is 4 halves times 3/1, and then you could square that. You could square the 4, square the 2, square. I mean, you can do whatever you want. But anyway, so this is 1 squared divided by 3 squared, and that's 1 divided by 9. So that's kind of how you can square fractions mentally just a lot faster. Sweet. And then so this is going to be 1/9 v naught squared. So cool. We're going to put that into here. We're going to have 1/2. And in the problem, they just kick these out. So 1/2 times 1/9 mv naught squared. So now we came in with 1/2 m naught v squared, and we left with, you would write it like this, 1/9 1/2 mv naught squared. So you could say, you know, this is where it's good to get good with fractions for these problems. You'd be like, hey, we did come in with 9/9 1/2 mv naught squared, and then we left with 1/9 1/2 mv naught squared. So the difference, it says what's the loss in energy, and it's just the loss in energy of this neutron. It's the loss in kinetic energy of the neutron. Now, knowing that it put its energy into this, how do you say this? Deuterium. Yeah, there you go, deuterium. So the energy went into the deuterium, increased in kinetic energy. It had a kinetic energy initial of 1/2 mv squared, and it had 0 velocity. So it had 0 kinetic energy, but then gained kinetic energy for that one. All right, hell yeah. So sweet. We did the first problem. Oh, and so I guess we didn't really do it. The first problem, what's the change in kinetic energy? Well, and it says loss. So the change in kinetic energy is going to be the final, a smaller number, minus the initial, a bigger number. And so we're going to have negative 8/9. You know what I mean? 1/2 mv naught squared. So this is the change. But we're going to have a loss. And so if they're just saying what's the loss, that's kind of an absolute value. So our loss is 8 divided by 9. And I don't know how you do 8 divided by 9. Yep. I mean, I'm trying to find different ways to do mental math faster. I mean, you could just say 8 plus 1 divided by 9 plus 1 is pretty close. So that's going to be 9 divided by 10. So you're going to be pretty close to 0.9. And so that's where this value... All right, hell yeah. So that's where this value right there is close to 0.9, and this value right here is close to 0.9. So the answer is either one of those. And yeah, it was tricky for me. The decimal is right there. It's just a weird place to... I thought this was 89 or something and 28, but now the decimal's right there. Okay, so now we have to do this same jazz with a carbon, and a carbon has a mass of 12. So, but hell yeah, we're on a roll. You know what I mean? So let's have this mass be 1, and then we're going to do a mass of 12m. We're going to come in with initial velocity, and when we leave, you know what I mean, hey, this mass will have v1, and then this will have v2. Now, if you were to do this by the book, you would call this velocity u1, you would call this velocity u2. No, I'm sorry, you would call this velocity u2. And then you would say the final velocity would be v1, and then the final velocity right here would be v2. Oh, okay. No. So they did it. They did it close enough to the book. Instead of saying this was u1, they just said v0, and this is 0 anyway. So okay. So now I'm a little bit more satisfied with their notation. But yeah. So and we're going to use that coefficient of restitution of 0. So we know that the difference between, and it's the relative velocity, this is 0, and so the relative velocity here, v0 to 0, has to match the after the collision, and so we have that equation that says v2 minus v1 is equal to v0, is equal to, the difference here. Sweet. Oh, and shoot, am I already... Oh man, this is kind of bumming me out. Is I'm not in... I didn't do the negative sign. So when I said this, the difference between the relative velocities between this would be 0. So the relative velocity here would be 0 minus v0, which would be negative v0. And the difference here would be v2 minus v1. And so we should have these equal to each other, but no, we don't, because the equation is like the reciprocal. It's let's write the equation. The equation basically says the final velocities. So we would have v2 minus v1. Now you could just do, and then you would divide by not the initial u2 minus u1, but it would be this minus this. It would be the opposite, v0 minus 0. So this is the equation that gets you E. If you did the opposite way, you would have v2 minus v1 divided by and it's the ratio. It's the ratio of the velocities leaving compared to the velocities. Now is that right? Yeah. Yeah, and this is a cool way to know how to stack this fraction. Because the relative velocities leaving could be 0. You know what I mean? So this number could be 0. You wouldn't want to divide by 0. So the difference between the initial velocities, which we could say is 0 minus v0. So this is going to give us a negative number, but this is going to be negative E. You know what I mean? So that's typically how you would see this in a textbook, and how they would write in a textbook. You would have this, v2 minus v1 is equal to negative E, and then you would have this velocity, u1 minus u2. So, so it's not the difference between these two, it's the reciprocal of the difference between these. All right, so hell yeah. So it is just total awfulness, because how are you going to remember that? And but at least you know the downstairs portion of this fraction has to be the relative velocities between the two things colliding. Because if things collide, they are for sure going to have a difference in velocity. That's going to be a positive value. And if they stick together and that elasticity is 0, or you have an inelastic collision, well, the relative velocities between these, the top part's going to be 0. Cool. You just need to know that this bottom part is the first minus the second, because if you do the second minus the first, you're going to get a negative, so coefficient of restitution, man, they should always have this as a negative, coefficient of restitution being a negative number. I don't know. But yeah, that's why these collisions totally suck. There's just a lot of little details to remember, and that's in 2 years I'm not going to remember. In 2 months I'm not going to remember that. All right, so let's dive in. So we have, if this is 1, then we can bring this upstairs. I mean, all we really want to know is that the difference between the velocities. Yeah, I mean, and it's kind of cool how you can, well, I have, yeah, damn it. I mean, you could always just say the first velocity, the one that you're interested in coming in, this, just say this is the positive. If this is the positive direction, then you're going to say that, yeah, so that, if that number is positive, and then it's the difference between the other ones. I think I can remember that. Because then we get the equation that this V naught is equal to the difference between these two. So you got V2 minus V1. And that works. Because this would be negative 1. And, no, in this case, this would be negative 1. And this is a negative down here. We would multiply this negative with that negative, and we would just have V naught. So we would have V naught is equal to the difference between those. Holy Toledo. Alright, so that's our equation for the coefficient of elasticity. Now we just want the momentum equation, which is this mass and times the velocity. This is stationary, so the initial momentum, this doesn't have any, but this initial has to equal the final, and so that's going to be this mass with this new velocity m1 plus 12m times V2. We can drop the m's, and we're going to have V naught is equal to V1 plus 12 V2. We can solve this equation, and let's solve it for V2. I thought that was easier. So we're gonna do V2 is equal to V naught plus V1, and we're gonna put this equation right into here. We need 12 V2, so let's just do that right off the bat. So we got 12 V naught plus 12 V1. And so we're going to plug that right into there. And we can just kind of do it all at once. We're going to have, hey, 13 V1 over here. So 13 V1. We're going to have 12 V naught. I guess I can just write that, 12 V naught. Try not to do too many steps at once. What are we trying to solve for? Well, let's... we're trying to solve for this V1 in terms of V naught. So let's get this over here. So we have 1 subtract 12. So we're going to have negative 11 V naught is equal to 13 V1. So let's solve for V1. And so we got V1 is equal to negative 11 13ths V naught. Okay, so, and this shows that because this is now massive, we did this scenario where if this was the Earth, hell yeah, the Earth does move that way, but hardly at all. So with a perfectly E is equal to 1 collision, the downward velocity is going to equal the upward velocity. And they're gonna, both balls are going to start and end at the same height. And that's going to be the scenario where, hey, it doesn't look like this moves at all, but this maintains. It's almost, this is basically 1. So 11 divided by 13 is very close to 1. And so, you know, when this comes in, it hits and then bounces. Sweet. And so now we're going to satisfy this equation. Because we have a negative of a negative, V2 is, so we're going to have, I guess, V naught is equal to V2 minus a minus, so we're going to have plus 11/13 V naught. Solve for V2. V2 is equal to, I'm just going to make this 13/13, and then subtract 11/13. So yeah, this is 13/13 V naught, and then we're going to subtract over here 11/13 V naught. So V2 is going to be 2/13 V naught. Hell yeah. So like it's not going to move very much. And now let's do a check on reality that we have mv naught is our initial momentum going in that has to equal our momentum going out. So we're going to have a negative 11/13 mv naught going that way, and then we're going to have this way, we're going to have added to 12 times 2, so we're going to have 24/13 mv naught going that way. So we have 24 minus 11. Oh, did I do this wrong? No. Yeah, 24 minus 11 is 13. So we were going to have 13/13 mv naught. That's mv naught is equal to mv naught. So we have a check on linear momentum, and we have our velocities. So I'm not going to do this problem 4 times, but we're going to use these linear velocities. Oh man, I think I just want to get to it. I don't want to print out any more pages. Yeah, and then the commenter was like, hey, can you do like 20 to 30 of these things real fast? And it's just like, not my style. You know what I mean? I'm learning a lifetime of knowledge just on this one problem. And I don't know. Some people are faster. They can just be like, yep, I know the equation. But I don't know. I think you really have to kind of get your feet wet. All right, so we do have these velocities. And so we need to know the kinetic energy initial of this mass. And we're going to have 1/2 mv naught squared. Cool. And then the kinetic energy final of this neutron after it hits, well, it's going to maintain a lot of its kinetic energy. And so we have this negative 11/13 v naught. That's going to be v1 because kinetic energy final is 1/2 mv1 squared, because that's the final velocity of this. It's going in the opposite direction. We have a v1 squared. This is v1, and so we're going to square it, and we're going to have 121. Is that 11 squared? And then this is going to be 169. Hey, I'm pretty good at this. And then we got v naught squared. Sweet. So so this is the number that we're going to have, 121 divided by 169. Yeah, and holy Toledo. Okay, so yeah, let's run with it, and then so that's going to be our kinetic energy final is going to be 1/2 times 121 divided by 169 v naught squared. And then so the difference between these is going to be like this. The kinetic energy initial now is 1/2 169 divided by 169 v naught squared. And so we lost some energy, not very much. So we just lost 169 minus 121. And so that's 8. This is 4. Yeah, we just lost 48 divided by 169. 48 169ths. And this is where you're just like, well, is that 0.28? I don't know. You know what I mean? Let's say it was 0.25. So we're going to have basically 50. And if this was 0.25, we would have 200 here. And I mean, that's close enough. And this would only be 0.25. But if we had 0.28, we would need to make this number smaller, you know, so then we would have 50 divided by like 180, and maybe that would be closer. So we can see that this is probably this 0.28, you know what I mean? And how would, yeah, I don't even know how to, yep. Yeah, that's tricky. Now we could use the method. Let's see if I can use this method. It'd be kind of fascinating. We have 48 and we got 169. I'm going to add 31 to this, and then I'm going to add 31 here. Kind of a weird thing to do, but then we're going to get 200, and 48 is going to go to 9, and then we're going to get 79. And so then I can just half this. Now I can say that this is 79 divided by 2. That's going to be 35 plus 4. So, I mean, yeah, so it's going to be, holy Toledo. Yeah, 70, half of 70 is 35 plus 4. So we have 39. So 39 100ths. No, that was a horrible. So that would be 0.4. But at least that is going to be higher than 0.25. But that wasn't a very good way to guess. Anyway, so let's just throw that into our calculator. So we have 48 divided by 169, and we get 0.28. There you go. So so that's going to be the energy loss, and so here's our answer. So when we got the carbon atom, our energy loss is going to be 0.28. That's going to be the fractional loss. All right, that was brutal, and I spent a lot more time on the collision part of this problem than knowing the kinetic energy. But there's so many problems that, hey, relate velocity. Like, hey, we have a velocity initial, velocity final, and then of two different systems. You know what I mean? System 1, and then system 2. And, you know, you need to relate their kinetic energy. Like, hey, if this decreases in velocity, you know, and this increases, let's say this decreases, this increases, you know, this halves, this doubles. It's because this energy is 1/2 mv squared. That velocity term is going to be a factor of 4. So, yep. So if your velocity decreases by a factor by half, your energy is going to decrease by a factor of 4. So might as well do that. So if we have 1/2 mv naught squared, and then we have a kinetic energy final of 1/2 m, and then we have 1/2 v naught squared. This term is going to be 1/2 m 1/4 v naught squared. And then you can see that this is the difference. We started with, and you can rewrite this as 1/4, probably out in front. That would be probably the more sensical way, 1/2 mv naught squared. And then you could write this initial velocity as 4/4 1/2 mv naught squared. So you can see that we have a loss of 0.7 of 3/4 of 75%. All right, and that was kind of interesting because I said if we half the velocity, our energy decreases by a factor of 4, and sure it does. Our energy started at a full 1, and then we went down to 0.25. But the energy loss would be 0.7, like would be a 75% loss. So there you go. So you would have a energy reduces by a quarter. But the energy loss is 75%. So I guess those are things that, yeah, we just go back and then, play the mental game of like, oh, yeah, if they're asking for energy loss, it's not going to be the reduction in energy. It's going to be the, the amount compared to the initial. And so that's a 75% reduction. All right, sweet. Okay, so I think I'm done with this. That was not fast at all, but I think it was very productive. And productive for me going over this stuff. This equation sucks. Anytime you have a negative, And then you have, but this negative is useful. If you use the negative, then it's the difference between the velocities. And then we talked about how you can stack them. This is never going to be zero, because if you have a collision, you're obviously going to have something approaching something else, and the relative speeds between them is going to be a positive value. So in the denominator, that thing's not going to be zero. But this top part can be zero because they can stick together, and that would be an elasticity of zero, or they can bounce back. And they can only do that. They can only bounce as much as, so that's probably the last thing, is you have the Earth here, and you have this velocity incoming, this velocity naught. After it hits, this ball cannot, you drop it from that height, it cannot reach that height. Because to reach this height, it would have to have a velocity of greater than v naught, and that would be an e of 1.1 or anything greater than 1, 1.2. You just can't have that. Because linear momentum has to be conserved. You're coming in with mv naught. This thing, sure, the mass of the Earth doesn't move, but then you can't leave with a momentum of m something greater than v naught. M greater than v naught. You can't have that. So, all right. So that shows you where, this elasticity is a number between 0 and 1. Cool. All right. Thanks for joining me on this one, and that's a video.